All right, welcome everybody. This is the joined us of Scala Bay and Vancouver Scala meetup. Through the mercy of virtual world, we unite a lot of communities. And I'm Alexey Krabarov, the founder and organizer of some of this. And we're very happy to have with us today Michael Pilquist, coming in from Philadelphia, who is a veteran Scala developer and architect. And he was a speaker at our meetups and conferences, so we're very happy to welcome him back with a talk on fs2.Chunk. And the second talk will be by Giovanni Joseph, who will talk about Apache Pulsar. And when he recently published a book about it and its transactions. And so they're both Scala developers. Take it away, Michael.
All right, great. Thank you for having me. This is actually my first time speaking at SF Scala, but not my first time at Vancouver. So really pleased to be back in that sense. So today's talk is about fs2.Chunk. The fs2.Chunk data type is a bit of a workhorse of the fs2 streaming library, but it tends not to get that much attention from the conference circuit, if you will. It's a basic data type, but nonetheless, I think there's some very interesting design decisions that went into it over the many years I've been maintaining the library. So without further ado, let's jump right in. So what is a chunk? A chunk, to prepare for this talk, I went and sort of did the Rich Hickey style, go to a dictionary and grab a definition of something. In this case, my dictionary is the Scala doc of fs2. And so I grabbed these two lines from the beginning of the Scala doc of chunk. So a chunk is an immutable, strict, finite sequence that supports efficient lookup. Okay, this gives us a bit of a feel. It's immutable, right? We're functional programmers, we like immutability. We've got this funny strict thing, which we'll talk a bit about today. So hold on to that one. It's finite. We have a streaming library. So if we need to do like infinite streams, we can always, emit chunk after chunk after chunk. So our individual collection type that carries elements can be finite. And then notably, it has this efficient indexed lookup. So this definition is interesting, but it's a bit lacking. And I say it's a bit lacking because really this is satisfied by vector. Really are satisfied by any index sequence in the Scala collection library. So why don't we just use vector as the main data type in the fs2 library? Let's take a look at these two capability traits. So here I have one trait socket that has like a reads operation that gives us maybe a potentially infinite stream of bytes coming from a network socket. And I have a files capability trait that lets me read, some bytes from a path on disk. In both of these cases, I get an fs2 stream back that evaluates, any number of effects in the effect type f and gives us bytes, gives us individual bytes. Streams move chunks of elements around, not single elements, right? A stream is like a vehicle of chunks, is one way to think about it. And yet, our type here is a stream of f comma byte, not like a stream of f comma byte vector or list of bytes or something. So we want this nice compositional API that lets us look at streams as sort of these infinite sequences. But for performance reasons and for efficiency reasons, we're going to move around densely packed sets of elements at a time, right? The other sort of interesting thing just with this first set of capability traits is that both of these two stream types really represent some type of operating system, IO type interaction, right? We're reading things from the networks. We've got some maybe kernel interactions here. In both cases, you can imagine probably things like maybe Java IO direct byte buffers interacting with our underlying operating system. And so we want to find a way to have as minimal copying as possible. We don't want to take the individual byte buffers that maybe come back from a networking API and move all of their contents into, let's say, a vector. And yet, when I got first involved in this library back in like 2014 or so, maybe 2015, that's exactly what it did. The emit constructor of, at the time, what was called process, what is now called stream, emitted a sequence of elements. And when you looked at the implementation of emit, it basically wrapped elements in vector. So I would do performance tuning. I was working on applications at the time that did like MPEG-2 video processing, processing like big transport streams worth of video content. And I would have maybe performance issues and look at things in the profiler. And one of the things I noticed was garbage collection pressure as a result of lots and lots and lots of tiny vectors. So what I have here is a chart. On the vertical axis, we have different data types. We have vector in Scala 2.12 and prior, vector in 2.13. For anyone that didn't know, there was quite a bit of performance work put into the 2.13 standard library, improving vector. And then a primitive array of bytes, and then the fs2.Chunk of byte. And then on the horizontal axis, I have like the size of each of those collections, from empty, to a single element up to 10,000 elements. And what I'm measuring here in this chart is like the memory size, the heap allocation for a collection of that size. And so some things are kind of interesting here. On the far left, for empty collections, you can see array and chunk are each the same at 16 bytes apiece, but like a 2.12 vector is 56 bytes for each empty vector. A singleton vector is 216 bytes in Scala 2.12, but only 24 bytes for a primitive singleton array and 32 bytes for chunk, right? And as you move to the far right, there's other interesting things. In particular, when we talk about bytes, right, a primitive array of bytes is going to be densely packed, but a 2.13 or 2.12 vector is really going to store bytes in object arrays, right, in like a tree of object arrays. And so we have a bunch of wasted space as a result of those object arrays storing boxed bytes. And you can see that pretty clearly in a roughly 4x increase in storage space. So chunk, we can see here, is competitive, within a constant factor of primitive arrays. So we need to augment our definition a little bit. It's not sufficient to say that a chunk is just immutable and strict and supports index lookup. We also want a chunk to be memory efficient for both small and large collections. And we want a chunk to avoid copying, just like we saw in that network example. Defer that copying unless it's absolutely necessary. So let's walk through these properties one by one and sort of build up a representative version of chunk. Since this is a slide and not the actual cross-building code, I can use Scala 3 and I don't have to use any braces. Otherwise, this is going to be representative of the types of things you'll see in the fs2 code base. So a chunk is finite. It has a known size at all times. There's no such thing as an infinite chunk. And that size is a 32-bit integer. This is unlike, let's say, a bit vector from scodec, where our sizes may be longs, right? Maybe 64-bit longs. If you have a use case where you need more than a 32-bit integer, then you can always emit 2 chunks or emit n chunks in a fs2 stream. A chunk has this efficient random access. And so when we say efficient, that's sort of a loaded term. What do we really mean by that? In this case, we've chose to implement it in this way. A chunk, just like an index sequence in the standard collections library, or just like an array, is going to have an index-based apply method that returns the element directly. I'm a functional programmer at heart. I want my functions to be total, and yet, it's the second function we've added to chunk, and I've defined it in a non-total way, right? I can pass an index that's out of bounds, and you can probably guess what's going to happen. We're going to have to throw an index out of bounds exception. We don't wrap the result in option in this case, because the access patterns we want to support are really index-based access patterns, looping through elements with while loops, as an example. And so we don't want to force all usage of the indexed API to be going through sequencing or traversing or otherwise wrapping and unwrapping options. All right, so we're already going to start making a little bit of a trade-off in our design space. So how about that memory efficiency property? How are we going to implement that? Here's a bunch of constructors. We have a constructor for an empty chunk, and in fact, it's a val. It's a single val that's shared, just like nil in Scala for lists, right? Chunk.empty is a single chunk. It's got a fixed size, right? That's how we manage to keep that to the minimum object footprint. We have a singleton constructor that just wraps a single value of type A, right? So all we're paying for in this case is the reference to that single value of type A on the heap and the object header of this instance of chunk. Again, that's why that was just, just slightly larger, right? Just only 24 bytes on the heap. And then this third one maybe is a little bit more interesting. We have an array constructor, which wraps an underlying Java array. And note in particular, we don't do defensive copying, right? So this is sort of a handshake agreement to get immutability. If you construct a chunk via the array constructor, and then go and mutate the underlying array that you gave us, that chunk is no longer immutable. But that's a trade-off we've decided to make in the design of chunk to get the performance characteristics that we care about. And we've got a few other like that. We have the ability to wrap any index sequence, including vectors. Again, we don't need to copy those elements. If you have an index seq that's already got already constructed with all of your elements, there's no need to move them into an array, just to wrap them into chunk. And likewise, we have support for network APIs like Java and IO byte buffer. And again, byte buffer, like the array case, is not doing defensive copying. You might say, well, wait a minute, that first line of that method looks like it's duplicating the buffer. But if you have not used the Java NIO API, that's only duplicating the sort of cursors that point to the underlying data. That's not duplicating the raw data itself. So again, we don't make defensive copies in this case. So consider this example. Maybe we have some API that gives us, a few megabytes worth of data from the network. We store that in this val huge. And then we've got usage that maybe looks like this. Someone says huge.take10, take 10 bytes from that. And then maybe again, they say huge.drop10. So we want to minimize copying. In this case, maybe we don't want to iterate through twice. So maybe instead, we'd write that with split. And so in this case, we say huge.split at index 10. We get a prefix, we get a suffix. And now we have an access pattern that's pretty common when writing stream combinators. The access pattern is like process the prefix, do something with it. Maybe we're parsing bytes into text or doing some type of framing of a binary protocol. But we're going to process that prefix. And then when that operation completes, we're going to go and store off the suffix, maybe wait for more data to come in from the network, right? And then further process that later. And so the challenge here becomes, how can we ensure that that suffix doesn't have to do a full memory copy of the data stored behind that chunk? The way we do it is via this array slice constructor. So this is just an example of structural sharing. The idea is that, array slice itself will store an underlying array and then store a starting offset in that array, as well as a count of elements from that offset. When we look up an index in this, we're just going to, shift the index up to the offset. And then we can implement split at in a constant time, zero copy way. right? We can say if the index that we're asked to split at is in bounds, then we fall through to this last else case, and we just have two array slice constructors, right? Both of which are constant time. So we get a free, from a copying perspective, we get a free implementation of split at. But what did we give up by doing that? One thing we gave up is this notion of strictness, right? Normally with a chunk, we said we want all of our operations to be to execute immediately, not to be deferred the way like maybe a view would be in the standard collection library or an iterator, right? So we want all of our operations to sort of execute as soon as they can. And in this case, we're really delaying the copying, right? We're delaying the copying because it's, in most cases, a good trade-off for the performance of most applications. So we'll talk about, how to deal with it when that's not the case. But we sort of have given up a little bit of this notion of strictness. Similarly, we've given up a little bit of predictability, or maybe as a result of the loss of strictness, we've given up predictability around memory footprint. If someone is given a chunk that has size 5 or size 10 from some arbitrary function, they might think that that chunk is only taking a small amount of heap space, when in reality, it may be an array slice pointing to an absolutely enormous underlying array. Right? So we've given up a little predictability in our reasoning around the memory footprint of our chunks. So we'll come back to that. But before we do, let's look at the implementation of a few combinators on the chunk type. So the first is the simplest. It's ForEach, the same ForEach that we see on list and on any other collection. Because we have constant time size and constant time apply, we can implement ForEach for all of the different constructors of chunk as just a simple while loop. And in fact, FS2 for a long time had these while loops inlined in all of the different operations on the chunk data type. I'm thinking that like inlined while loops, you can't get faster than that, right? Like it's the compiler is going to do some vectorization magic and it's just going to be great. And we had recently switched all of that back to implementing all of the combinators in terms of ForEach and ForEach with index, which we'll look at it in a second, and actually got a performance boost. So it's sort of interesting hotspot optimizations going on there. All right, we have ForEach with index. Same idea, right? It's a while loop. We just pass the index I to the function as we walk through the elements of the chunk. So now with these two, we can start implementing more interesting combinators like map. The same map that you know from any other functor, including list, vector, so forth. And maybe our first implementation of map looks something like this. We go and allocate an array of B of a given size. We know that the map isn't, mapping a function over all of the elements in a chunk isn't going to change the size of the thing that we return. So we can use the size of this chunk to allocate our target array. And then we just run through, iterate through all the elements using ForEach with index and apply each element to our function and store the result in the corresponding array index. But this doesn't compile. And it doesn't compile because we can't construct an array for some generic type B, right? The compiler complains. It says, hey, you don't have a class tag. In order to create an array, you need a class tag for element type B. So we do what all good programmers do. When the compiler complains about that constraint, we just add a constraint to the function. So in this case, we have this function. I changed the name of it to map concat now instead of map. And I picked up this class tag constraint. And now this works absolutely fine. The body of the function didn't change at all. It compiles, it's performant. There's no problem with this definition. Why did I call it map compact instead of map? Partially because I don't really want to redefine what it means to be a map function, right? Partially because when you look at like a functor map, if I have a functor instance for chunk, I want map to have no constraints. I don't want it sort of limited in a certain way. You can only be a functor if you can provide me this class tag constraint in some way. So partially for that reason. But there's a bunch of other reasons as well. And in fact, map compact doesn't exist at all in the library. We don't have this function in fs2. One of the reasons is that function 1 itself is not specialized for very many types. Now note, as of now, Scala 3 doesn't support this, but 2.13 and prior, you can see is not specialized for byte in the return type or in any of the parameter types. So just by the very nature of using this higher order function map, you're going to do a bunch of boxing and perhaps a bunch of unboxing depending on what your target collection type is. Right? Maybe more important than like function specialization and runtime characteristics is the fact that class tags, virally propagate. If our caller is also in a generic context, meaning like they're parameterized by some type parameter A, and they call map on a chunk of A, they might not have a class tag for their target type B, and so they might have to pick up that same constraint, and those constraints start propagating up the call stack, typically until you reach a point where you have a concrete target type. From an API design perspective, this really forces folks to have to make a hard decision. If you're using chunk and you need to call the map operation, if you got one version of map that doesn't have a constraint, you got another version of map concat that takes a class tag, now you have to make the same trade-off for yourself. Like, should I pick up the constraint on my own type parameters and use the fancier version? Or should I drop that constraint and use the one that maybe is less performant? And then finally, and this is the sort of the real kicker, is that we're going to run into the same problem over and over again in the various combinators we define on chunk. And we can't make this same decision, of splitting, of having a concat or a dense version that uses a class tag, as well as a version that doesn't use a class tag and just stores things some other way. We can't make that same dual operation for every single combinator. So we need something that's orthogonal to this, right? We need a way to implement map, first of all, such that it doesn't require a class tag constraint, but then also to opt into getting this compaction behavior. So let's first implement map. The trick is the following. It's the same trick that's used in the Scala collections library. You don't normally see it because it's hidden way deep down, but it's the same trick that's used. So in essence, we are going to create an array of any, right? So we're going to have an object array. We're not going to use a primitive array in this case. And yes, that means if you were mapping like to a byte, like your B type here was instantiated to be byte, then that means we're wasting some space, right? Because now we've got maybe 4-byte, array elements instead of 1-byte array elements. However, note what I mentioned about function 1 not being specialized 1 byte. Things are already boxed. So from a performance perspective, maybe that doesn't matter, even though a storage perspective is a different thing. Okay, so we construct this array of any. The rest of the function looks basically the same until the very end, where we cast our chunk of any back to a chunk of B. And of course, this is completely unsound, right? The only way we can make this work is if we absolutely guarantee that this underlying array is never directly accessed as an array of B. If it is directly accessed as an array of B, things might work. Things might throw an array store exception. Things might throw a class cast exception. So we have to be very careful that this array is kept as an implementation detail only. But as long as we can manage that, this does in fact work and is safe on the various platforms we compile to. All right, so we have a version of map that doesn't need compaction, but how do we get compaction if we really care? Like if we have a densely packed object array now of bytes, and we know we're wasting all of that space, we want to maybe compact it back down in certain cases. So here's how we do that. We have two operations. We have a way to convert any chunk to a primitive array. And in this case, we'll just pick up that class tag constraint. This looks very much like map, except we're not taking a function, right? Their original version of map. So we just picked up a class tag constraint. And that generally doesn't have the same disadvantages as picking up the class tag constraint on map path. The reason I say that is that if from a caller's perspective, if you're trying to convert a chunk to an array, it's because you want like a primitive array. Like you want to go and allocate a byte array because you're about to pass this byte array off to a, some input-output library or something that works in terms of byte arrays. So just the cases in which this come up, the use cases in which you want to do this, end up being cases that already align well with either being concrete or having access to the necessary class tag. And then of course, if you want to just compact a chunk, we can do that by just wrapping the result of toArray in an array constructor. Now, in reality, in the library, these operations are much more complex because we do a bunch of performance enhancements here. There are cases where, like, if we know the internal array that's used in the array slice is already a primitive array, and we know that the target array that you want to move to is the right primitive type that matches, then we can do like a bulk array copy instead of moving elements over one by one. And there's other specializations for various constructors of chunk, but this is the general idea. All right, a few more operations. How about filter? Filter is sort of like map, right? We're going to run through all the elements, apply each element to a predicate, and keep all the ones, and the predicate returns true. In this case, we don't know the size of the array to construct, but we can use the collection library's mutable array builder. If you haven't used mutable array builder, you should. It's awesome. It's basically Java's array list. It starts small and then grows by powers of 2, using underlying arrays behind the scenes. So in this case, we create an array, we create an array builder, but we have the same class tag issue. So we're just going to jump, use the same trick, jump right to the solution. We're going to create an array builder for any. Now we pass a size hint. We say, we feel like most of the time when people filter chunks, they're going to keep most of the elements. And of course, that's not always true. Of course, there are cases where you filter out all the elements or filter out most of the elements. We sort of feel like, most of the time that's a good, common use case. And so in that case, we're going to give a size hint to be equal to the current size of the collection. This is going to avoid a bunch of the intermediate copies as the array builder starts small and then starts doubling in size as we add elements while we iterate, right? And then, we iterate through the collection. If the predicate passes, we add the elements. Eventually, we call b.result and dump all of those, all of those elements back into a single array. And array builder will do the right thing. If the target collection has fewer than the size hint, then it will do the copy if it has to. If it's exactly equal, it doesn't do the copy itself. Okay. Okay. So with combinators like that, maybe the next design choice we have to make is what to do about copy, or how can we discourage bad usage patterns which might have undesirable performance. So let's look at this example. Again, we have some huge, maybe multi-megabyte chunk, and then we have some tiny little chunk, in this case, like a character return line feed, just 2 bytes. And here we're using stream.Chunk, which is like how you get a stream of elements from just one individual chunk. But like these two programs here, stream.Chunk of huge concatenated with tiny little CRLF, that program is the same as the second program, which says lift the huge chunk into a stream and then concatenate another stream to that, which is the result of lifting this tiny chunk into a stream. So we want the bottom one to be the one that folks write naturally. We want the line 4 to be the one that's sort of avoided because we don't want this copy occurring, right? So we take advantage of the fact that as programmers, we like things that are elegant, right? We like things that are simple and look nice. And so for the pattern that we don't want folks doing, we just make it ugly. We make it difficult in a sense. We add friction, as one of my colleagues likes to say. So we have this chunk.concat method, which takes a sequence of chunks. In particular, we're just not providing that ++ method on chunk, right? Because if it's there, then folks will use it, but they might not think about the fact that they're actually getting, copies of data. So let's look at chunk.concat. So we take this sequence of chunks, we take our class tag constraint, we scan through our sequence of chunks, adding up all their sizes to come up with the total size. We allocate an array of that size, rip through them, maybe copying chunks, directly into the array by offset using some copy to array operator that I'm not going to show you. Fairly straightforward. Okay. What could go wrong with this implementation? Well, let's look at a potential use case for it. So this method, uncons ends, got a lot of syntax. Don't worry about all the types. It's not entirely important. Let me just describe what this method's going to do. This method does exist in the library in fs2. It's very common. What uncons ends says is, given some stream of elements, S here, stream of elements of type O, and given a desired count of elements N, pull on that stream until we accumulate exactly those N elements. And when we've acquired those N elements, emit it as a single chunk, just one chunk of those N elements, and then also give us the rest of the stream in case maybe we want to process that more later. So this type of like request northbound for N many elements, then go do something, very common pattern in stream libraries. So to implement this, we're going to use recursion. So we're going to have this internal sort of loop function, go. And what go is going to do is accumulate constituent chunks, right? Because our source stream might be giving us individual chunks, like chunks with just one element. It might give us empty chunks sometimes. It might give us huge chunks that are much bigger than what was asked for, right? So we're going to accumulate all these small chunks until we reach our size N. And then we're going to call go recursively, building up this accumulator until we reach the right size. So here on line 10, we say pull from the source stream. That's what this s.pull.uncons does. If the source stream is empty, we get this none. In which case we say, well, we couldn't get all of the elements you wanted, so we'll just give you everything we've gotten so far. So we're going to return chunk.concat with an empty stream since we reached the end. But instead, if we've got some element, some chunk from the source stream, and then some tail remainder stream, then we've got a couple conditions you got to deal with. If that head chunk is less in size than the desired remaining number of elements, then just queue it up, stick it into our queue, and call ourselves recursively, right? Decrementing our target size by however many elements we just got, right? And if not, if the head size is greater than or equal to our desired size, then we're going to use that split at combinator we wrote. We're going to split the one we got into a prefix and a suffix. We're going to queue up the prefix into our accumulator and then concatenate all of those into a single output. And then we also are going to take the suffix and cons it onto the remainder stream, right? Since we didn't quite need to process that stuff yet. So what goes wrong with this implementation? The issue here, again, is that class tags virally propagate. And so uncons n, in order for that previous implementation to compile, would need to pick up a class tag constraint on type O. And that is an absolutely valid approach to solving this problem. In fact, I tried it recently again. despite this method existing for something like 9 years. Unfortunately, this combinator ends up being really common. Like I said, it's used all over the place in streaming libraries. Maybe you don't use it directly, but a bunch of operations that you do use directly use this, right? And so it really starts propagating all throughout the library. You end up picking up this class tag constraint. Another option is to change the game. Move the goalposts. Don't concatenate, right? We're accumulating these constituent chunks into a queue. Maybe we just change our return type to just return that queue. Okay, valid option. Might be okay, might not be okay, depending on the use cases for this method. One of the problems with this approach is that the total size that has been accumulated is no longer constant time. Like whoever gets this queue of chunk, if for whatever reason they need to know the total size, they're going to have to scan through that queue and add up all of the element sizes, right? A third option is we could remove the class tag constraint from concat with a similar trick like we did with map. So let's take a look at that. We have this concat tagless implementation. Basically, don't take the class tag constraint and instantiate an array of any. Otherwise, everything seems fine. But we do have this primitive boxing behavior, the same primitive boxing behavior we have with map. And unfortunately, this one does start to have a performance issue. When you look at the use cases for things like uncons n, this does show up in a lot of places, right? So even though it's the exact same trade-off that we had with the map operation, when you look at realistic use cases for these operations, it ends up the trade-off ends up not being as much of a win. So how can we fix this? Well, we had this implementation for years, which I've now called concat2clever. Concat2clever basically said, well, what if we could test and validate that every element of every constituent chunk is a certain primitive type, right? So the algorithm here looks something like this. It says, if the input chunks for every one of the constituent chunks, they only contain bytes, then call the version of concat that works with a class tag using bytes, using the byte class tag. We're going to have an if-else like that for every primitive type. Now, of course, that's a linear scan. Maybe it's not a big deal, right? Maybe like when you think about concat from like an asymptotic behavior, it's going to be linear anyway, right? And as we all know, like when it comes to performance, all we ever care about is asymptotic behavior, of course, right? We don't care about constant time. So who cares if we have to do 2 passes through our data? No, of course not. That's terrible. So, performance is a challenge. We had a performance solution. One of the ways in which we avoided double scans is we had this contains only method that had a shortcut to say if the target chunk knows for a fact that it has an element type of a certain type, basically picks up and stores a class tag, then we can do that with just a single check instead of having to look at all of the elements inside of that chunk. So okay, like that buys us a certain amount of constant factor performance. But really, what killed this approach was JavaScript. This is a fictional JavaScript REPL. But if you haven't done a lot of JavaScript, then maybe this comes as a surprise. But there is no primitive types in the JavaScript runtime, right? Like the value 1, if you have a lot of experience in the JVM, you think that's a primitive int. So clearly, a primitive int is not an instance of byte. But on JavaScript, all of the primitive types are number. And these instance of checks all pass. And so this was spotted by, I believe it was Ross Baker when he was doing some work with HTTP4S, reported some class cast exceptions in chunk that should never have occurred, but it was all because of the performance optimizations in concat and not realizing that they would completely break on JavaScript runtimes. So the real solution, this is what exists in the library today, is none of the above. It's sort of option 2 where we shifted the goalposts. But it turns out if we just change the result type to be a queue of chunk, it ends up being a little bit difficult for everyone to use. So what if we made queue of chunk a subtype of chunk? Here's what that looks like. So in the chunk companion object, we have a new constructor, queue. Queue is going to store a Scala collection immutable queue of constituent chunks. Okay. And it'll also store the accumulated size of all of the elements inside of that. So now we've been able to restore that constant time size operation. If someone wants to do something with size, they're guaranteed that it's constant time. It's not going to be a scan of our constituent chunks. With this definition of queue, we can have both, prepend as well as appending chunks. We do have a pretty important performance trick here, which is that we don't allow empty chunks in our constituent queue. So all of our constructors, these two, as well as the main constructor for creating one of these queues, all of them are going to elide any of the empty chunks from ever getting inside of the chunks queue. And I'll talk about why that's important in a little bit. But then with this definition, we have to implement index-based lookup. And index-based lookup in this case is going to be a recursive loop through the chunks queue, through that constituent chunks queue, right? So it's basically going to say, start at the head element. If the target index is within those bounds, then do the lookup. Otherwise, recurse on the tail. Adjust the offset for the size of the element the size of the constituent chunk we just skipped over. Okay. With that definition, then we can finally add our ++ method to chunk. We no longer need to discourage usage of ++. Again, we have to do a little bit of logic to make sure empty chunks are handled correctly and efficiently. But nonetheless, we get an efficient ++ operation. And so then uncons n ends up being able to be implemented in a pretty straightforward way. We don't need a class type constraint. We no longer need a chunk queue. Our accumulator is just a plain old chunk of O in the same way you might write something with vector. And in the various cases where we needed to, emit that, in this case here, we no longer need to concat anything. We just emit the accumulator. And likewise, when we add elements to our accumulator, it's just via ++. In fact, uncons n doesn't even need to be aware of the existence of this chunk queue constructor. It's only going to use this ++ operation. Okay, so you may have spotted the issue with this approach, though. The question becomes, what is the asymptotic runtime performance of that apply operation? Right? Well, let's think about it. If the constituent chunks, if the number of constituent chunks in the queue is much smaller than the total number of elements in all of those constituent chunks, then we have, effectively constant time lookup, right? If the total size is 100,000 elements, but there's only, 5 constituent chunks, then yeah, technically it's, linear in the number of constituent chunks, but it's dominated so much by the size of the collection that we can say it's effectively constant time. But as the number of constituent chunks approach the total size, then that lookup algorithm becomes linear, right? And this happens when each chunk has size 1. Now note it can't get worse. It can't get worse than linear. We don't allow those empty chunks to show up in the chunk queue. If we did allow empty chunks, then we would have a harder problem to deal with. We don't allow empty chunks in the chunk queue. So absolute worst case, all of them have size 1, and our apply operation becomes a linear scan. Okay, maybe that's not a big deal. Well, what's the runtime performance of ForEach? Remember, ForEach and ForEach with index are used in map, are used in filter, are used in a few dozen combinators on Chunk. So what's the asymptotic runtime of ForEach? Well, looking at the implementation, we see it's just a linear scan of the elements by their index. And so, when the constituent chunk size is small compared to the total size, then this still remains O of n. But when the average constituent chunk size is size 1, we've now turned ForEach into quadratic behavior, which then means map and filter and all of those operations are quadratic. So that's bad. We released this. We put this in production and then had someone find it, unfortunately. All right, so what's the fix? Well, fixing ForEach ends up being really, really simple. We don't need index-based lookup to implement ForEach. We don't need index-based lookup to implement ForEach with index. In both cases, we can get linear lookup regardless of the behavior of apply by just doing nested ForEaches and doing nested ForEach with indexes, right? And in fact, if it wasn't for that inlining I mentioned of all of the while loops before, then this would be a great reason to do it, right? Like if map was implemented with its own while loop, we could inline that while, or we could get rid of that inlining of that while loop and instead just have it call ForEach, and in that way get linear behavior back. But we did say one of our defining characteristics of Chunk was the efficient lookup by index. So can we restore a nicer asymptotic runtime there? So we can, and this is an algorithm that Diego, one of my co-maintainers on FS2, came up with. But the general idea is that we're going to compute 2 lookup tables, right? The lookup table is simple. It's just all of the accumulated sizes of the chunks up into that index in the table. And I'll give an example of this in a moment. But if with that lookup table, we can then do a binary search by index. And when we find the right cell, then we can go and grab the chunk at that same index and do a direct lookup of the target value there. So what do I mean by that? Here we have a chunk queue of 5 chunks. The first is size 3, the second is size 10, and so on. We'll create a lookup table with consisting of 2 arrays side by side. The accumulated sizes array, you can see, starts with size 3 because this has size 3. The second element will have size 13, right? 10 plus 3. Next we'll have size 14, and so on. And then we'll also, in this table, have a chunk array that just references each element in the queue, so we don't have to walk it again to find each chunk. And our apply operation looks something like this. We say, like, let's go and do a lookup for the element at index 20. So what the algorithm needs to do is find the smallest accumulated size that is greater than 20. And it finds this element 34 here and returns index 3. And so we say, okay, short of a boundary condition, that means the target index is in this a corresponding chunk. So move to the chunks table here. That takes us up to this chunk here. And now we just need to offset our index by the total number of elements prior to this chunk, which is just available here. So we take 20 minus 4, we get 6, and we return the 6th index of this particular chunk. The implementation is not complicated, it's just a little wordy. We pre-compute these lookup tables, but we do it with a lazy val inside of the chunk queue. So we have this lazy val that is only accessed on apply, when apply is called. Just rips through and instantiates those lookup tables, nothing really fancy. And then on a call to apply, there's a couple cases here we deal with. Like if you try to access the head element, we have special logic because that's really common. If you try to access the last element, we also have special logic because that's really common. But if you try to access any element between those, we then go and implement the algorithm we just talked about. So we build the accumulated sizes, lookups. If it hasn't been built yet, we binary search them. And then we handle the various edge conditions to make sure it's not like the last element in the previous chunk, things like that. So what's the runtime of this implementation? Well, the very first time we call apply, ignoring the optimizations for the head element and the last element, the first time we call apply, it's going to be m log m, where m is the number of constituent chunks, right? And it's m log m because we pay 1m for building the lookup tables, and then we pay a log m for the binary search. But then all subsequent calls are just log m. And in our worst case condition, where the average constituent chunk size was 1, that means our overall lookup here is an amortized log n. So wrapping up, we mostly delivered on the properties of our chunk data type. And I say mostly because we did give in certain ways, right? A chunk was immutable except for when it wasn't, right? Except for when you constructed it with a mutable array and played games with that array. It was mostly strict except for when you're doing things like split at and take and drop. And certainly it's mostly efficient with index-based lookup unless you really care about that logarithmic parameter. But that's okay. One thing that I think maybe this talk does, and which I don't want to encourage, is that it may give you the impression that the design of chunk was a series of logical decisions, right? Looking at how what are the impacts of this particular design choice, and how does that change usage, etc. And this is clearly absurd, right? This process was like an 8-year process. In designing this talk, I went and looked up how many bugs we had in chunk over the last few years. I got tired of clicking, the older button in the GitHub user interface, but I collected like these 18 or 19 issues. I think over a 3-year period, I think is roughly where these come from. But the state of the data type today is the result of hundreds, thousands of folks using it in all sorts of different domains, all sorts of different use cases, and really us finding those sweet spots of where it really aligns well, where the default decisions, the default behaviors of the data type align with the needs of the user base. And in fact, when designing this talk, I ended up putting 4 additional PRs in to improve performance in various ways. We're just putting out this plainly made us realize, oh wait, we can do this a little bit better. And so, overall, I hope that gives you some type of insight into at least, my journey in the design of this data type. Like I said in the beginning, it is a relatively simple data type, but just because it's simple, it doesn't mean there aren't tons of challenges built into it and tons of opportunities for improvement. And hopefully that journey shows the way in which we can lay out a constraint-based design approach. Here are the things that we want our type to do, but then know when to sort of bend and twist and push and change the overall constraints that we're working with. So anyway, that's the end of my talk today. I'm happy to take a couple questions, but otherwise I'll hand it over.
Thank you very much, Michael. That was a great talk. Folks, feel free to ask questions.
Can we ask it like on audio? Yeah, okay,
Yep.
So, right, no, great talk, and thanks a lot, and interesting to see these internals and the journey, right? So, yeah, quick question like that. So, random access property of the chunk. I'm not sure I'm grasping that it's really needed like random access. It feels to me that we're still always accessing it like in sequential manner, but what is important that it's like unfragmented piece of memory to provide like good like cache CPU pipelining thing, but no really random access is ever happening in the internal implementation. Is this correct? Or sometimes we do like like random access on the chunk in implementing something interesting.
Yeah, no, I think that's correct. When we actually introduced the performance issue by making chunk.q a subtype of chunk, I mean, we knew that was a risk. It wasn't like that surprised us. It did surprise us that folks had access patterns where the average constituent chunk size was 1 and cared about it, right? Like that, we knew that would come up, but we didn't think it would end up mattering. We didn't think folks would run into a use case where they were actually running like combinators over it. What surprised us, I guess, was, or we didn't really put together, was that all of those operations on chunk had those inlined while loops, right? So, someone calls map or filter or something, and they're really have this random access looking access pattern, but they really don't care about that. They really just wanted ForEach, right?
Yeah, okay. So it's really what triggers random access. It's inlined while loops, right?
Exactly.
Yeah, I hear.
And really, I mean, that was because I think folks thought, again, like, how could you do better than a while loop? ForEach is clearly going to be slower because it's going to be like a Lambda, creation or whatever, a stack frame, etc. In practice, we've seen the opposite, or at least.
No, of course, internally, right? This is all about while loops, right? Also, what's interesting for me, I mean, that's probably, yeah, so it was vector initially, that was like internal structure. But again, this is like in Scala, this is still some kind of a tree, right? Or try, whatever, right? And so it's important to understand that underlying thing is actually array, which is unfragmented, continuous piece of memory, right? Which is a very good decision point, yeah. No, thanks a lot. Thanks a lot. This is interesting.
Absolutely. Actually, and one of the things that's perhaps interesting is that arbitrary updates of elements or patching of elements is not that use case is not supported by chunk, whereas like vector does that very well, right? Because vector has that 32-way tree and can just patch in with just the impacted node. We avoid that because it's not a use case we need, and as a result, we can get densely packed large structures.
Exactly, good old array, right? It makes sense.
Any other questions? If not, let's thank Michael. It was a great talk.
Thank you very much.